what happens at the end? Exploring the universe's finale blends cosmic marvels with deep thinking, intriguing both scientists and philosophers similarly. As we ponder the end of the universe, we dive into a realm where numbers and scientific ideas mix with questions about existence. Come along as we explore this captivating journey into the universe's ultimate fate. One prominent theory, backed by extensive scientific evidence, emerges as a front-runner in this cosmic puzzle: the Big Freeze, also known as the heat death of the universe. This theory finds its roots in thermodynamics, a branch of physics dealing with heat, temperature, energy, and work. The Big Freeze scenario revolves around the second law of thermodynamics, which states that in an isolated system like the universe, entropy, a measure of disorder or randomness, tends to increase over time. According to this theory, as the universe expands, driven by the enigmatic force of dark energy, it gradually cools down as its energy disperses across a growing volume. Eventually, all stars will exhaust their nuclear fuel, fading into darkness. Galaxies will drift apart, and over immense timescales, black holes will evaporate. In the distant future, the universe will reach a state of maximum entropy, where there's no significant energy exchange, rendering it uniformly cold and dark. This Big Freeze scenario is the most probable outcome according to our current understanding of cosmology, particularly based on measurements of cosmic microwave background radiation, the lingering light from the Big Bang, and observations of the universe's accelerating expansion. These observations suggest that the universe is flat and will likely keep expanding indefinitely. While this paints a bleak picture of the universe's far future, it's important to note that this isn't something imminent, but rather something that will unfold over an incredibly vast span of time beyond our grasp. We're talking about timescales in the trillions of years, far surpassing the universe's current age of about 13.8 billion years. Our understanding of the universe's fate has evolved significantly over the years thanks to advancements in technology, astrophysics, and theoretical models. This journey began in the early 20th century with astronomers like Edwin Hubble, whose observation of the redshift in light from distant galaxies provided the first solid evidence of the universe's expansion. This discovery was pivotal, shifting scientific consensus away from the belief in a static universe. In the following decades, scientists wrestled with the implications of this expanding universe. Early models suggested that if the gravitational pull of all matter was strong enough, it might eventually halt expansion and lead to a big crunch, where the universe collapses back in on itself. This theory suggested a cyclic view of the universe, where each collapse, or crunch, would be followed by another Big Bang, and the cycle would repeat. However, in the late 1990s, observations of Type Ia supernovae, extremely bright and distant stellar explosions, brought surprising new evidence. These observations not only confirmed that the universe is expanding, but also revealed that this expansion is speeding up. This acceleration hinted at the presence of a mysterious force called dark energy, which seems to oppose gravity, causing the universe to expand faster and faster. The discovery of dark energy marked a significant shift, leading to the prevailing theory of the Big Freeze, or heat death. According to this theory, the universe will keep expanding endlessly. Over trillions of years, energy will spread out more and more, causing the universe to gradually cool and dim. Additionally, modern cosmology has been transformed by detailed mapping of the cosmic microwave background radiation. This leftover radiation from the Big Bang offers crucial insights into the universe's early conditions and its subsequent evolution. Studies of the CMB support the notion of a flat and accelerating universe, supporting the Big Freeze idea. On the other hand, the Big Crunch theory offers a captivating and dramatic scenario for the universe's ultimate fate. It presents a counterpoint to perpetual expansion, rooted in the principles of gravity. According to the Big Crunch theory, the universe's expansion, initiated by the Big Bang, will eventually slow and reverse due to the gravitational attraction of all matter and energy. This would result in a gradual collapse of the universe, pulling galaxies, stars, and eventually all matter back toward a singular point. This theory draws upon principles from general relativity and posits that the universe's destiny is closely linked to its density. If the universe's density is high enough, all the gravity from stars, galaxies, and other cosmic objects could eventually outweigh the force pushing them apart. This would cause the universe to stop expanding and start collapsing back in on itself. As it contracts, temperatures would skyrocket, potentially undoing the effects of the Big Bang in a kind of cosmic rewind. The collapse, known as the Big Crunch, would end in a state of extreme density and heat, similar to the universe's early moments after the Big Bang. Some theories even suggest that this collapse could trigger another Big Bang, proposing a cycle where each collapse is followed by a new expansion phase. However, recent astronomical observations have cast doubt on the Big Crunch theory. The discovery of the universe's accelerating expansion implies that the influence of dark energy outweighs the gravitational pull of all matter. This suggests that the universe might keep expanding forever, making the Big Crunch scenario less likely according to current cosmological models. The Big Rip and the Big Crunch are two different theoretical scenarios for the universe's end, each with vastly different processes and outcomes. The Big Crunch involves the universe's gradual collapse, driven by the gravitational pull of matter and energy. If you're still watching, please like the video and turn on notifications for the channel so you don't miss our weekly documentaries. Moving on. As the collapse progresses, everything in the universe gets compressed into a single, incredibly dense point. This theory relies on the idea that the universe's density is high enough to counteract its expansion, aligning with principles from general relativity. However, it has become less favored due to observations indicating the universe's accelerating expansion. On the opposite end of the spectrum, we have the Big Rip theory, which suggests that the universe's expansion not only persists, but speeds up indefinitely due to dark energy. Here, dark energy eventually becomes so dominant that it overwhelms all other forces, including gravity and electromagnetic forces that hold everything together, from galaxies down to atoms. As the universe rapidly expands, it reaches a point where these fundamental forces can't keep structures intact anymore. Galaxies would tear apart, followed by the breakup of individual star systems, planets, and eventually the very essence of matter itself. The Big Rip ends with the universe torn apart at its most basic level, resulting in a sparse, cold, and dark state with particles scattered far apart. The main contrast between the two theories lies in their driving forces. The Big Crunch is pushed by gravity, leading to a collapse, while the Big Rip is propelled by a relentless acceleration of the universe's expansion due to dark energy. Furthermore, the timelines for these events differ greatly. The Big Rip would happen relatively quickly once it gains momentum, unlike the Big Crunch, which would unfold over a longer period. Both theories showcase the intricate and ever-changing nature of the universe, offering different viewpoints on how its story might conclude. While current observations hint that a Big Rip might be more plausible than a Big Crunch, these are still speculative ideas in cosmology. Now let's talk about the concept of heat death, also known as the Big Freeze. This idea is rooted in thermodynamics, specifically the second law, which says that the total disorder or entropy of a closed system can't decrease over time. In the universe's context, this means that entropy keeps rising until it reaches a peak. The heat death scenario envisions a future where the universe expands so much that all energy is evenly spread out. This uniform energy distribution results in no thermodynamic free energy, meaning no more useful work can be extracted from the system. In simpler terms, it's like a battery fully drained of power and unable to recharge. In this scenario, stars will run out of fuel and stop shining, leaving behind remnants like white dwarfs, neutron stars, and black holes. Eventually, even these remnants will fade away, with black holes evaporating due to Hawking radiation. Galaxies will drift apart, and the universe will become vast, cold, and dark. Temperature differences, which drive energetic processes, will disappear. Without these variations, no energy transfer can happen, leading the universe to a state of maximum disorder and equilibrium. At this point, all known physical processes would stop. The heat death scenario is seen as the most probable outcome based on current cosmological models, which consider the universe's observed accelerated expansion. This expansion, fueled by dark energy, suggests that the universe will keep growing, eventually dispersing all matter and energy. Black holes, mysterious and powerful cosmic entities, are key players in theories about the universe's end. Their unique characteristics offer insights into the universe's long-term fate. In the Big Crunch theory, black holes could hasten the universe's collapse by exerting significant gravitational pull. They might merge and grow larger, accelerating the universe's contraction towards a denser state. However, in the heat death scenario, black holes mark one of the universe's final stages. After stars die out and galaxies disperse, black holes remain. Over vast time spans, even black holes evaporate, emitting Hawking radiation. This process is slow but inevitable, contributing to the eventual dispersal of all matter and energy. As black holes evaporate, they gradually lose mass until they disappear entirely. This slow evaporation could be one of the last events in the heat death scenario for the universe. As black holes emit Hawking radiation, they contribute to the universe's increasing disorder. When the last black hole vanishes, the universe would be left extremely cold, with almost no energy and lacking any significant structure, a stark contrast to its fiery and dynamic beginning. Studying black holes and their characteristics like event horizons and singularities helps us understand the fundamental nature of space-time and quantum mechanics. These understandings are crucial for developing a more complete theory of the universe's fate, especially in bridging the gap between general relativity and quantum physics. Dark energy, a mysterious force captivating scientists and the public alike, plays a vital role in determining the universe's future. It's a type of energy present throughout space that speeds up the universe's expansion. Scientists first inferred its existence from observations of distant Type Ia supernovae in the late 1990s. These observations showed that the universe's expansion rate is actually increasing over time, contrary to previous beliefs. Known forces of gravity acting on visible matter alone couldn't explain this acceleration, leading to the hypothesis of dark energy as an unknown repulsive force. Dark energy is one of the biggest mysteries in modern cosmology. It's invisible and doesn't interact with light, making it super tricky to spot directly. Scientists have come up with different theories to explain it, from ideas like Albert Einstein's cosmological constant to more complex concepts involving new fields and particles. Dark energy is super important for the future of the universe. If it keeps on being the main source of energy, like current observations suggest, it's going to have a huge impact on what happens next. Dark energy's push is making the universe expand faster and faster, leading to possibilities like the Big Rip or the heat death. In the Big Rip scenario, this push gets so strong that it tears everything apart: galaxies, stars, planets, even atoms. In the heat death scenario, the ongoing expansion makes the universe colder and emptier as stars and galaxies move farther away and lose their energy. With dark energy calling the shots, the universe might just keep on expanding forever, getting bigger, colder, and lonelier as time goes on. This marks a shift from earlier ideas like the Big Crunch, where the universe's expansion would eventually halt and reverse. But how do we measure the universe's expansion rate? Measuring this rate, known as the Hubble constant, is a fascinating process that involves advanced technology and keen astronomical observations. One primary method involves looking at the redshift of distant galaxies. As galaxies move away from us due to the universe's expansion, the light they emit shifts towards the red end of the spectrum. By measuring this redshift, astronomers can figure out how fast these galaxies are moving away from us. To determine the universe's expansion rate, astronomers use specific objects called standard candles. These are objects like Type Ia supernovae, which explode with a consistent brightness. By observing how bright these supernovae appear from Earth, scientists can estimate their distance. The farther they are, the fainter they appear. Similarly, Cepheid variables, a type of star with a predictable brightness pattern, serve the same purpose. By measuring these distances and matching them with the speed of galaxies' movement, astronomers can work out the universe's expansion rate. Another method involves studying the cosmic microwave background, the leftover radiation from the Big Bang. By analyzing the CMB's small temperature changes, astronomers can figure out various aspects of the universe, including its expansion rate. This approach gives us a peek into the universe's early days, which offers a different angle from studying far-off galaxies today. Also, baryon acoustic oscillations, BAO, regular periodic patterns in how visible matter is spread out, come into play. By examining these patterns and the universe's large-scale structure, astronomers can figure out how quickly the universe was growing at different times in its history. There's also a newer method called gravitational lensing that helps with these measurements. This happens when a massive object, like a cluster of galaxies, bends the light from things behind it because of its gravity. How much the light bends can tell us about how fast the universe is expanding based on the universe's shape, which is influenced by its expansion rate. Each method has its own complexities and limits. Interestingly, they sometimes give slightly different answers for the Hubble constant, which has caused a bit of confusion in cosmology called the Hubble tension. Quick reminder to subscribe if you haven't already, so you can keep up with our future astronomy documentaries. Thank you so much. Now let's talk about dark matter's role in the universe's end. Dark matter, a mysterious but crucial part of the universe, is key in theories about how the universe will end. Even though we can't see dark matter and it doesn't give off or absorb light, we know it's there because of its gravity's effects on things we can see, like stars and galaxies. Understanding dark matter is vital for predicting what will happen in the end. In the big picture of the universe's fate, dark matter's main influence comes from its gravity. This mysterious stuff makes up about 27% of the universe's total mass and energy, way more than the regular stuff we see, like stars and planets. Its gravity has been super important in shaping how the universe is structured, pulling stuff together to form galaxies and groups of galaxies. In scenarios like the Big Crunch, dark matter's gravity could be a big deal. If dark matter's pull is strong enough to counteract the universe's expansion caused by dark energy, it could make the expansion stop and even reverse. In such a situation, the universe would stop getting bigger and start getting smaller, eventually squeezing all matter into one tiny, super-dense point. But recent observations, especially of how the universe's expansion is speeding up, suggest that dark energy's push is stronger than dark matter's pull. This makes the Big Crunch scenario less likely for now. In the heat death idea, dark matter still plays a role, but it's not as active. As the universe stretches out and cools down, dark matter, just like regular stuff, spreads out more thinly. Its gravitational pull weakens as galaxies and groups of galaxies move farther apart. In a universe headed for heat death, dark matter sticks around, but its power to shape how the universe looks and works fades away over time. Understanding dark matter's part in the universe's end helps us grasp how the universe changes and grows over time. It's like a cosmic support structure, shaping how galaxies and groups of galaxies form and move. But because dark matter is so mysterious, we're still not sure about a lot of its properties and what it means for the universe's long-term future. Now, let's look into thermodynamics a bit. Thermodynamics is a branch of physics all about heat, temperature, and how they're connected to energy and work. It's really important in figuring out what happens to the universe in the end. The laws of thermodynamics, especially the second law, are key to theories about how the universe will keep changing until it reaches its final state. The second law says that in a closed system, like the whole universe, disorder or randomness always increases over time. Applying this to the universe means that its disorder keeps going up until it hits a maximum. This growing disorder has a big effect on what happens next. As disorder increases, the energy we can use to do things goes down, until we reach a point where there's no more significant energy changes possible. We call this heat death or the big freeze. In this state, the universe hits a kind of energy balance, with energy spread out evenly everywhere and no more heat moving between different parts of the universe. This even spread means that all processes relying on energy differences like star burning, structure formation, and even life would stop. The idea of increasing disorder also links to how the universe expands. As the universe gets bigger, matter and energy spread out more, leading to more disorder. If the universe keeps expanding forever, as suggested by our current understanding of dark energy, this spreading out would keep increasing disorder, eventually leading to heat death. Additionally, the second law of thermodynamics might affect the flow of time. In our everyday experience, time moves in one direction from past to future, just like entropy increases. Some physicists think the growing disorder of the universe might be connected to how we see time moving. So, if we know all this, what stops us from predicting how the universe will end? When trying to predict the universe's fate, our models run into several limits because of the huge complexity of space and our current scientific knowledge. These limits are crucial to recognize because they show where our understanding still needs work. One big limit is our limited grasp of dark energy and dark matter. These mysterious parts of the universe are key to how it changes, but we don't know much about them. Dark energy, which speeds up the universe's expansion, can't be seen directly, and we figure out its properties from its gravity's effects. This means our models are missing some pieces as we're working with an incomplete picture of what the universe is made of. Another challenge comes from measuring distances and phenomena in space. The universe is incredibly huge, and figuring out distances, speeds, and other space stuff across such massive scales is really tough and can have mistakes. For instance, when we use things like Type Ia supernovae as standard candles to measure distances, there's a whole bunch of steps involved, each with potential for mistakes. The Hubble tension is a big example of these measurement issues. It's about how we get different values for the Hubble constant, which shows how fast the universe is expanding when we look at early universe stuff compared to stuff nearby. This difference suggests there might be things we don't know about affecting the universe's expansion, showing our models have limits. Also, our big theories like general relativity and quantum mechanics have their own limits. These are the basic ideas of physics, but they haven't been fully put together yet, especially in really extreme situations like black holes or the start of the universe. Since we don't have all the answers, our predictions might not be right in these extreme cases. Lastly, science is always changing. What we know about the universe has changed a lot over time and will keep changing. New discoveries, better technology, and new theories could totally change how we see the universe. How does entropy tie into the universe's end? Entropy, a concept from thermodynamics, is key to understanding how the universe will eventually fade away. Simply put, entropy measures how messy or disorganized things are in a system. The second law of thermodynamics says that in a closed system, like the universe, entropy always goes up over time. This steady rise in entropy has big implications for the universe's future. As the universe changes, it naturally heads towards a state where entropy is at its highest. This means all the energy in the universe gets spread out evenly. In a universe with maximum entropy, energy is everywhere, but there are no differences in energy to drive changes or do work. This state is often called heat death or the big freeze. In this scenario, stars, which rely on energy differences, like when hydrogen turns into helium through fusion, would run out of fuel and stop shining. Over billions and billions of years, all the leftovers from stars would cool down, black holes would vanish because of Hawking radiation, and the universe would become a big, cold, dark place with hardly any structures like galaxies or stars. This idea of increasing entropy leading to heat death is different from an older idea in cosmology called the Big Crunch, where the universe's expansion would stop and then reverse, ending in a collapse back to a single point. The heat death idea, based on the second law of thermodynamics, suggests a slow, steady decline into disorder and balance. It's worth noting that the timeline for the universe to reach maximum entropy is incredibly long, much longer than the universe's current age of 13.8 billion years. Understanding entropy and its role in the universe's end not only gives us a glimpse into the distant future of the cosmos, but also highlights the fundamental laws of physics guiding its journey from the Big Bang to now and beyond. What are some other ideas about how the universe might end? Exploring these alternative theories takes us into the realm of creative and advanced cosmology. While these ideas are more speculative, they offer fascinating possibilities for the universe's future. One idea is the cyclic or oscillating universe theory. This suggests that the universe goes through endless cycles of expansion and contraction. Picture the universe expanding from a Big Bang, stretching out for billions of years, then contracting back into a dense state only to explode outward again. This rhythmic pattern challenges our usual understanding of how the universe unfolds over time. Another captivating concept is the multiverse theory. This broadens our view beyond just our universe, proposing the existence of many, maybe even infinite universes. Each of these universes could have its own laws of physics and unique features. In this context, the fate of our universe might be just a small part of a vast, ever-changing multiverse. Then there's the Big Bounce idea, a variation of the cyclic universe concept. Instead of a series of big bangs and big crunches, the Big Bounce suggests a universe bouncing back from a highly compressed state, rebounding into expansion instead of collapsing into a singularity. This model often brings in elements from quantum theory and offers a smoother transition from one phase to another. Lastly, there's the theory of vacuum decay, or the false vacuum collapse. It presents a dramatic and sudden way for the universe to end. In this theory, our universe exists in a false, unstable vacuum state. Suddenly, it could transition to a true, more stable vacuum, rewriting the laws of physics and drastically changing the universe's structure. This hypothetical event would spread at the speed of light, creating a new type of universe in its wake. How do faraway galaxies give us clues about the universe's future? Distant galaxies serve as cosmic guides, helping us see into the universe's future. When we study these galaxies, we're actually looking back in time because of how far away they are. This makes them incredibly useful for understanding not only the universe's past, but also what might happen down the road. One important way faraway galaxies inform us about the future is through their movement, particularly something called redshift. As galaxies move away from us, the light they give off gets stretched, making it look more red. This redshift helps us figure out how fast the universe is expanding. By measuring the redshift of different galaxies at various distances, astronomers can see how the universe's expansion rate has changed over time. This information is crucial for predicting whether the universe will keep expanding forever, leading to something like the Big Freeze, or if it might take a different turn. Another important aspect is how distant galaxies help us understand dark energy. This mysterious force, making up around 68% of the universe, is pushing its expansion faster. By watching distant galaxies move away from each other, scientists can learn more about dark energy. Studying its past effects on the universe's expansion helps cosmologists make educated guesses about its future influence. Distant galaxies also give us clues about the evolution of cosmic structures. By watching galaxies form and interact far away, we learn about how galaxies live and change, including when they merge. This knowledge helps us predict what might happen to galaxy clusters in the long term, including our own local group. Also, by looking at the light from these galaxies, astronomers learn about stars' lives and the elements in the universe. This tells us about how stars will evolve and how the universe's element mix might change over billions of years. The cosmic microwave background radiation is vital in cosmology, especially when we talk about the universe's end. This radiation is like a snapshot of the universe's birth, the Big Bang. It's a critical piece of evidence for understanding how the universe started and grew. The CMB shows us what the universe looked like when it was only 380,000 years old. At that point, it had cooled enough for electrons and protons to form hydrogen atoms, making the universe transparent to radiation for the first time. Even though the radiation has cooled to microwaves due to the universe expanding, it still holds a lot of information. One of the big jobs of the CMB is helping us measure the Hubble constant. This constant tells us how fast the universe is expanding. By studying the CMB data, scientists figure out how fast the universe expanded at different times. This data is super important for testing and refining ideas about the universe's future, like the Big Freeze or Big Rip scenarios. The CMB also tells us about the universe's shape and what it's made of. By looking at temperature and density differences in the CMB, astronomers calculate how curved the universe is and estimate how much ordinary matter, and dark energy there is. This helps us predict how these things will affect the universe's expansion and what might happen in the end. The discovery of the cosmic microwave background was a significant milestone in confirming the Big Bang theory, which forms the basis for many cosmological ideas about how the universe might eventually end. Essentially, the CMB tells us that the universe started out hot and dense, providing a crucial starting point for understanding its past and potential future. Studying the CMB in detail also helps to narrow down the possibilities for alternative theories about the universe's fate. Any viable theory must match up with what we observe in the CMB data. For example, theories suggesting a cyclic or oscillating universe need to explain why the CMB appears uniform and has specific properties that we see today. As for whether we can simulate or model the universe's end, it's a challenging but active area of research for astrophysicists and cosmologists. They're using cutting-edge technology and complex math to try to understand and predict how the universe might evolve and eventually come to an end. To simulate the universe's end, scientists need to accurately model the various forces at work, including gravity, dark matter, and dark energy. They do this by running sophisticated computer simulations that incorporate equations from general relativity. These simulations help visualize different scenarios, such as the Big Crunch, where the universe collapses back in on itself, or the Big Freeze, where it continues expanding indefinitely. For example, in simulations of the Big Crunch, researchers focus on how gravity might eventually overcome the expansion caused by dark energy. On the other hand, simulations of the Big Freeze project the current rate of expansion into the future, considering how dark energy will continue to push galaxies apart until all activity stops. Furthermore, scientists use these models to delve into the mysteries of dark matter and dark energy, two of the universe's most enigmatic components. By adjusting how these elements behave in their models, researchers can explore different outcomes and grasp how much the universe's fate hinges on them. While these simulations offer valuable insights, they're limited by our current grasp of the universe's laws and components. The accuracy of these models relies heavily on the data and theories they're built upon. For instance, any shifts in our understanding of dark energy or the discovery of new cosmic phenomena could significantly change the predicted results. Additionally, the immense time spans involved in cosmic evolution pose a challenge. These simulations often span billions to trillions of years, well beyond human lifetimes, making it hard to test and confirm predictions, keeping them largely in the realm of theoretical astrophysics. How does quantum mechanics affect our understanding of the universe's end? Quantum mechanics, the field of physics dealing with the tiniest particles, has profound implications for how we view the universe's ultimate fate. It introduces concepts that fundamentally alter scientists' perspectives on the cosmos, especially concerning its final state. One critical aspect where quantum mechanics plays a role is in the realm of black holes. Quantum theories, like those involving Hawking radiation, propose that black holes emit radiation and may gradually lose mass over immense periods. This concept suggests a mechanism by which even the most massive and long-lasting objects in the universe, black holes, could eventually vanish. In the context of the universe's end, this process could be significant, particularly in scenarios like the heat death, where black holes may be among the last structures remaining. Additionally, quantum mechanics introduces the idea of quantum fluctuations, small random changes in energy at a microscopic level. In a universe moving towards maximum disorder, as in the proposed heat death scenario, these fluctuations could have intriguing implications. Over unfathomably long periods, tiny fluctuations at the quantum level could potentially give rise to new particle arrangements or even spawn entirely new universes, as some theories propose. This introduces a layer of unpredictability and complexity to our grasp of how the universe might eventually end. Another area where quantum mechanics plays a crucial role is in our investigation of dark matter and dark energy. Despite their critical role in shaping the universe's destiny, we still don't fully comprehend their nature. Quantum theories offer potential insights into the characteristics of these elusive components, influencing our models of the universe's evolution. Furthermore, reconciling quantum mechanics with general relativity stands as one of the greatest puzzles in modern physics. This reconciliation holds the key to understanding extreme cosmic conditions, such as those prevailing in the early universe or within black holes. Achieving this synthesis could profoundly alter our predictions regarding the universe's fate, particularly concerning scenarios involving cosmic collapse or rebirth. What role does time play in theories about the universe's end? Time occupies a central and fascinating position in our contemplation of the universe's ultimate fate. In simple terms, time measures the progression and change from one state to another. In cosmology, grasping the nature of time is crucial for unraveling how the universe might unfold and eventually meet its end. Firstly, the vast temporal scales involved in these theories are mind-boggling. We're talking about billions to trillions of years into the future, surpassing all known human history, or even the universe's current age, estimated at around 13.8 billion years. For example, the concept of the heat death of the universe, where all cosmic activity ceases due to maximum entropy, is projected to occur over a time frame so immense that it dwarfs all known temporal measures. Time also intertwines with the notion of entropy, a fundamental concept in thermodynamics. The second law of thermodynamics tells us that entropy tends to increase in an isolated system over time, implying that as time advances, the universe should become increasingly disordered. This gradual increase in disorder guides our predictions about the universe's progression towards a state of equilibrium, where significant energy exchanges cease, ultimately leading to the heat death scenario. Moreover, in cosmology, time isn't just a linear progression from past to future. Theoretical models exploring the universe's fate often venture into the concept of time as a dimension entwined with the very fabric of space. In these models, the geometry and destiny of the universe are intimately connected with our understanding of time's structure and dynamics. For instance, in theories suggesting a cyclic universe, time might be viewed as a continuous loop, with each cycle of the universe's birth, expansion, and demise repeating endlessly. Additionally, time is crucial for understanding how cosmic structures evolve and decay. Processes like the lifespan of stars, the creation and disintegration of galaxies, and phenomena such as the gradual evaporation of black holes via Hawking radiation all unfold over time and contribute to the overall trajectory of the universe toward its eventual end. Now, how might the discovery of new particles change our forecasts? The detection of new particles could significantly shake up our predictions about the universe's fate, providing fresh perspectives and potentially reshaping our understanding of fundamental physics. Particle physics, the field that explores the tiniest building blocks of matter, has a track record of transforming our comprehension of the universe, and any new discoveries would likely continue this trend. Identifying new particles could yield crucial insights into dark matter, which makes up around 27% of the universe but remains one of its most enigmatic aspects. Currently, we can only infer the existence of dark matter through its gravitational effects. The discovery of particles that could be linked to dark matter would open up a new frontier in physics, allowing us to delve deeper into how this mysterious substance influences the universe's structure and evolution. This could, in turn, affect our theories about the universe's end, particularly if dark matter behaves differently than what we currently understand. Furthermore, new particle discoveries could illuminate dark energy, the perplexing force fueling the universe's accelerating expansion. Understanding the particle properties of dark energy, if it indeed has any, could be pivotal in foreseeing the universe's destiny. For example, if dark energy were found to vary over time, it might imply changes in the universe's expansion, potentially leading to scenarios like the Big Rip, or even a reversal to a Big Crunch. Another area where new particles could impact our predictions is in the realm of quantum mechanics and its interplay with general relativity. The discovery of particles with unexpected gravitational interactions or insights into quantum gravity could aid in formulating a theory of quantum gravity, a long-standing quest in physics. This could completely change how we understand extreme cosmic conditions, like what happens inside black holes or at the universe's beginning, and could influence our ideas about how the universe might eventually end. Moreover, discovering new particles might challenge or refine the standard model of particle physics, our best current explanation for the fundamental forces and particles in the universe. Any adjustments to this model could have big effects, reshaping our understanding of the basic building blocks of the universe and how they interact. The philosophical implications of the universe's end are as deep as they are diverse, touching on questions that humans have pondered for centuries. The notion that the universe could one day reach a definite end challenges our basic understanding of existence, time, and our role in the grand scheme of things. Firstly, thinking about the end of the universe makes us confront the idea of impermanence on a cosmic scale. For many people, the thought that the entire universe, including all its galaxies, stars, and even the atoms composing our bodies, might one day cease to exist or change beyond recognition is a humbling reminder of life's temporary nature. This can lead us to wonder about the value and meaning of our actions, civilizations, and even our pursuit of knowledge when faced with the vast, indifferent expanse of space. Additionally, theories about the universe's end also make us think deeply about time. If the universe is moving toward a state like the heat death, where everything stops changing, it raises questions about time itself. Is time an everlasting, continuous stream, or does it have a beginning and an end? These questions intersect with both philosophical and scientific debates about the nature of reality and how we perceive it. The idea of scenarios like the cyclic universe, where the universe goes through an endless cycle of expansions and contractions, also sparks philosophical reflections on eternity and the idea of things repeating indefinitely. This concept, suggesting that the universe and all its events could endlessly recur, prompts discussions about determinism, free will, and what makes human experience unique. Additionally, examining how the universe might eventually end delves into deep questions about existence. Recognizing that one day everything in the universe could cease to exist can stir up feelings of existential anxiety. However, it can also prompt a sense of freedom or a push to find purpose in the present moment. It encourages us to think about what it means to be alive in a universe that has limits and is constantly changing. Lastly, pondering the end of the universe urges us to reconsider our ideas about progress and our advancements in technology and science. It challenges us to think about humanity's role in the vast cosmos and prompts us to reflect on the impact we leave behind, not only on Earth, but also within the broader story of the universe. How have various cultures viewed the end of the universe? Throughout history, different cultures have offered their own unique perspectives on how the universe might reach its end, reflecting a diverse array of cosmological myths, religious beliefs, and philosophical concepts. These cultural narratives often blend science, philosophy, and spirituality, providing varied outlooks on the universe's ultimate fate. In Western traditions, heavily influenced by Judeo-Christian ideas, the end of the universe is often depicted as an apocalyptic event. This perspective, found in texts like the Book of Revelation, portrays a final judgment and transformation rather than a literal end of the cosmos. It emphasizes moral and spiritual conclusions rather than scientific details. Conversely, many Eastern philosophies and religions, such as Hinduism and Buddhism, propose a cyclical view of the universe. For example, in Hindu cosmology, the universe experiences repetitive cycles of creation, preservation, and destruction, known as Mahayuga. This cyclic process holds not only physical significance but also carries spiritual meaning, symbolizing the eternal rhythms of birth, life, and rebirth. Indigenous cultures across the globe also offer their own interpretations. Some Native American traditions, for instance, speak of a sequence of worlds or ages, each concluding with a transition to the next through various forms of renewal or destruction. These stories often highlight the importance of living in harmony with nature and recognizing the interconnectedness of all living beings, portraying the end of the universe as a natural and sacred part of a larger cycle. For instance, in Norse mythology, there's the concept of Ragnarok, a series of events that include a great battle resulting in the death of major gods and a world flood. After these cataclysms, it's prophesied that the world will emerge anew and fertile, with surviving gods reuniting and two humans repopulating the Earth. In modern times, as our scientific understanding of the universe has grown, these cultural tales have sometimes intertwined with scientific theories. For example, The notion of an expanding universe heading towards a cold, dark end may resonate with both apocalyptic and cyclical beliefs, seen as either the final state of entropy or just one phase in an ongoing cycle of cosmic events. Each of these cultural viewpoints not only reflects ideas about the end of the universe, but also deeper values and insights about life, existence, and the nature of change and continuity. They show how humans have long pondered not only the physical aspects of the cosmos, but also its metaphysical and spiritual dimensions, from its beginning to its end. Now let's delve into an intriguing hypothesis. The vacuum decay hypothesis is a captivating and somewhat unsettling idea in the realms of cosmology and theoretical physics. It proposes a scenario where the universe doesn't end with a bang or a whimper, but with a bubble. This hypothesis revolves around the notion of a false vacuum, a tentative or unstable state of space containing potential energy. In this scenario, our current universe exists in a false vacuum, a temporary and unstable condition that could decay into a more stable state, known as the true vacuum. This decay could be triggered by a random quantum fluctuation, creating a bubble of this true vacuum. What's particularly unsettling about this hypothesis is what happens next. This bubble would expand at the speed of light, altering anything it touches at a fundamental level. The laws of physics as we know them might completely change inside this bubble. Everything we're familiar with, galaxies, stars, planets, and even the basic components of matter, could be destroyed or drastically transformed as the bubble engulfs them. The vacuum decay theory is purely theoretical and not something we can expect to happen anytime soon. It's based on ideas from quantum mechanics and quantum field theory, which study how the universe behaves at its smallest levels. The theory suggests that what we think of as empty space might actually be filled with invisible energy fields. One interesting aspect is that this process could occur suddenly and without warning because it would spread at the speed of light. We wouldn't see it coming. But it's important to understand that this theory is just one of many speculative ideas about how the universe might eventually end. Can advancements in technology help us understand the universe's end better? Absolutely. Technological progress has always been crucial in expanding our knowledge of the cosmos, and it's key to uncovering new insights into how the universe might meet its end. As we develop better tools and computer models, our ability to observe, measure, and understand cosmic events improves, bringing us closer to answering some of the universe's biggest questions. One area where technology is making a big difference is in observational astronomy. New telescopes, both on the ground and in space, allow astronomers to see distant cosmic phenomena more clearly than ever before. For example, telescopes like the James Webb Space Telescope can peer deeper into space, potentially revealing new information about the early universe that could help us predict its end. Alongside observational tools, advances in computing are also crucial. Supercomputers can now process vast amounts of data and run complex simulations faster than ever. These simulations let scientists model different scenarios for the universe's end, from the Big Freeze to the Big Rip, with incredible detail. By tweaking variables in these models, researchers can explore a wide range of possible outcomes. Furthermore, progress in particle physics, aided by technologies like particle accelerators and detectors, helps us understand the fundamental forces and particles shaping the universe's behavior. Discoveries in this area could help us understand dark matter and dark energy, two crucial factors shaping the fate of the universe. For example, experiments at places like the Large Hadron Collider, LHC, might reveal new particles or phenomena that could change our view of the cosmos. Advancements in fields like quantum computing and nanotechnology also offer hope for cosmological research. Quantum computers, for instance, could tackle complex problems and analyze data in ways we can't do currently, potentially offering fresh insights into the quantum side of the universe and its eventual destiny. Supernovae are another fascinating aspect of studying the universe's end. These explosive events mark the finale of a star's life and are vital for understanding cosmic conclusions and the wider story of the universe. They aren't just visually spectacular, they're also treasure troves of information, helping astronomers unlock secrets of the cosmos, including hints about its eventual fate. When a star goes supernova, it shines brighter than entire galaxies for a brief period, emitting huge amounts of light and energy. This makes supernovae visible across vast distances, turning them into important markers in cosmic exploration. One of their significant roles is as standard candles. Certain types, like type Ia supernovae, always reach a consistent brightness at their peak, allowing astronomers to accurately measure their distance from Earth. By gauging the distance to these supernovae and their redshift, how fast they're moving away from us due to the universe's expansion, scientists can work out the rate of this expansion. This method led to a groundbreaking discovery that the universe's expansion is actually speeding up. This finding led to the theory of dark energy, a mysterious force propelling this acceleration. Studying supernova is like unlocking a cosmic treasure trove with profound implications for our understanding of the universe's destiny. These colossal explosions not only mark the dramatic end of stars, but also offer clues about the fate awaiting our cosmos. They shed light on the mysterious force known as dark energy, which holds the key to how the universe might end, whether it's in a big freeze, big rip, or another scenario. Additionally, supernovae have a crucial role in the cosmic recycling of matter. When they explode, they scatter heavy elements across space, which are vital for creating new stars, planets, and even the essential ingredients for life itself. In essence, supernovae symbolize both an end and a new beginning, echoing theories about the cyclical nature or ongoing evolution of the universe. Now let's talk about galactic collisions, these awe-inspiring events in the cosmos that actually contribute significantly to the universe's fate. Despite sounding tumultuous, these collisions are natural processes that shape the universe's journey. In the vastness of space, galaxies, held together by gravity, often encounter each other. These encounters range from gentle gravitational nudges to full-on mergers. When galaxies collide, it's not like a head-on collision on a road. Rather, they pass through each other due to the vast spaces between stars. Nevertheless, this cosmic dance has profound effects. One major consequence is the birth of new stars. As galaxies merge, their gas clouds collide and compress, sparking the formation of new stars in a spectacular display of cosmic creativity. This burst of star formation illuminates the merging galaxies and provides valuable insights into their life cycles and the processes driving star birth. Over incredibly long periods of time, galaxies collide with one another, which plays a vital role in their growth and development. The Milky Way, our own galaxy, has become as large as it is today, partly because it has merged with smaller galaxies in the past. This process is crucial for understanding what will happen to the universe in the far future. In a scenario known as the Big Freeze, where the universe keeps expanding forever, these collisions between galaxies might become rare as galaxies move farther away from each other. This could lead to a future where galaxies are isolated in a cold, expanding universe. These collisions also affect the way dark matter, a significant part of a galaxy's mass, is distributed. By studying these collisions, astronomers can gain insights into dark matter, which helps us understand the future evolution of the universe. One of the most anticipated galactic collisions in the distant future is between our Milky Way and the Andromeda galaxy, predicted to happen in about 4 billion years. This event will significantly change both galaxies, although it's not expected to directly affect any planetary systems, including our own solar system, because of the vast distances between stars. Instead, the merged galaxy, often humorously called Milkomeda or Andromeda Way, will mark a new chapter in the story of our local group of galaxies. Will studying exoplanets give us clues about the universe's end? The study of exoplanets, planets orbiting stars beyond our solar system, is a relatively new and quickly evolving area in astronomy. While exoplanets might initially seem distant and unrelated to questions about the universe's eventual fate, they actually provide valuable clues and insights into this cosmic puzzle. One significant way exoplanets contribute to our understanding of the universe's future is by shedding light on the formation and evolution of planetary systems. By observing a wide variety of exoplanetary systems, astronomers can gain a better grasp of how these systems develop over time. This knowledge deepens our understanding of how matter behaves and changes throughout the universe. For example, understanding the life cycle of planetary systems, from their formation to eventual demise, can offer parallels to the broader processes unfolding in the universe. Exoplanets also act as laboratories for studying the conditions that might lead to the end of planetary systems, which in turn informs our understanding of the ultimate fate of cosmic structures. For instance, studying exoplanets situated close to their stars and enduring extreme conditions provides insights into how planetary systems could be disrupted or destroyed. This research helps piece together a broader understanding of the stages leading to the end of both stellar and planetary systems across the universe. Moreover, exploring exoplanets enhances our comprehension of habitability and the potential for life elsewhere in the cosmos. Although not directly tied to the universe's ultimate end, this facet contributes to philosophical and scientific dialogues concerning the rarity of life and the evolution of the universe. It assists in framing our existence within a universe in constant flux and transformation. Additionally, studying exoplanetary atmospheres offers insights into the universe's destiny. By scrutinizing these atmospheres, astronomers discern their compositions and how they evolve over time under diverse cosmic influences. This understanding extends to how various cosmic conditions, such as radiation from nearby supernovae or the impacts of dark matter and dark energy, could shape planetary systems as the universe progresses. How does the large-scale structure of the universe affect its fate? The expansive structure of the universe, comprising galaxies, clusters, superclusters, and voids, profoundly impacts its destiny. This structure, molded by the distribution of matter and gravitational forces, isn't merely a static backdrop, but an active participant in the universe's ongoing evolution. A critical facet of this structure is its influence on the universe's expansion. Galaxies and cosmic structures are bound by gravity, influencing how they're distributed and move, thereby affecting the universe's growth dynamics. For instance, in densely packed regions like superclusters, gravitational forces can decelerate local expansion rates. Conversely, in vast cosmic voids with sparse galaxies, expansion proceeds relatively unhindered. The behavior of dark matter and dark energy, two enigmatic constituents of the universe, also significantly shapes the large-scale structure and consequently the universe's destiny. Dark matter, with its gravitational influence, aids in shaping and sustaining the cosmic web of galaxies and clusters. Meanwhile, dark energy propels the universe's accelerated expansion. The interaction between gravity and dark energy shapes how structures in the universe change and interact, which ultimately affects where the universe is headed in the long run. Additionally, the large-scale layout of the universe can help us understand its overall shape and structure, which is vital in predicting what might happen to it in the future. If the universe is closed, it could eventually stop expanding and start to collapse in on itself, leading to a potential scenario known as the Big Crunch. On the other hand, if it's open or flat, which is what current evidence suggests, it will likely keep expanding forever, possibly resulting in a big freeze or big rip. The way cosmic structures are spread out also has implications for how energy is distributed and how disorder, entropy, increases over time, which is crucial in theories like the heat death. As the universe changes over time, energy becomes more spread out across its vast expanse. The way the universe is structured affects how this spreading happens and how disorder increases over time, which is a big part of theories like the heat death. What role does string theory play in understanding how the universe will end? String theory, a field of physics that tries to bring together quantum mechanics and general relativity, offers a unique view on how the universe might end. It suggests that instead of tiny, point-like particles, the fundamental building blocks of the universe are tiny vibrating strings. While string theory is quite complicated and mostly speculative, it introduces ideas that could change how we see the universe and its future. One fascinating idea in string theory is that there could be more than just the 3 dimensions of space and one of time that we're familiar with. These extra dimensions could have a big impact on how the universe evolves over time. For example, how these dimensions change over time might affect how fast the universe expands, or even the nature of dark energy. String theory also explores quantum gravity, which is a field aiming to describe gravity using the principles of quantum mechanics. Understanding quantum gravity is crucial for explaining phenomena such as black hole singularities or the conditions during the early universe. When considering the end of the universe, a better grasp of quantum gravity could offer insights into how the universe might behave as it keeps expanding, potentially uncovering new scenarios beyond those currently favored, like the Big Freeze or the Big Rip. Furthermore, string theory introduces the idea of multiple universes or a multiverse. This notion suggests that our universe might be just one of many, each possibly governed by different physical laws. If this aspect of string theory proves true, it could profoundly change our understanding of the universe's fate. Our universe's destiny might only be a part of a much larger and more complex multiverse, where each universe has its own distinct end. What are the signs that indicate the universe is moving towards its end? Detecting these signs involves a blend of intricate astronomical measurements and theoretical predictions. While the end of the universe is a far-off event projected to happen over an immensely long timescale, there are observable phenomena that offer clues about its eventual winding down. One significant sign is the rate at which the universe expands. Astronomers measure this expansion by observing the redshift of distant galaxies, how their light stretches to longer, redder wavelengths as they move away from us. This redshift confirms not only that the universe is expanding, but also helps scientists determine how fast this expansion is occurring. The discovery of the universe's accelerating expansion was a crucial moment in cosmology, indicating the influence of dark energy. If this acceleration persists, it supports scenarios like the Big Freeze, where the universe would continue expanding indefinitely, becoming colder and emptier over time. Another indicator is the life cycle of stars. Stars are like the universe's power plants, and by studying how they are born, live, and die, astronomers can learn a lot about what the universe might look like in the distant future. As the universe gets older, the rate at which new stars are formed is expected to slow down, and the stars that already exist will gradually run out of fuel. By looking at galaxies that are older and where star formation has slowed down a lot, we can get an idea of what might happen to our own galaxy billions of years from now. The behavior of galaxies themselves also gives us hints about the universe's future. In a universe that's heading towards a cold and isolated end, we'd expect to see galaxies moving away from each other more and more over time. This means that the rate of galaxies crashing into each other and merging would also slow down. Telescopes that are very powerful can observe these movements and interactions, providing data that fits into our long-term models of what might happen to the universe. Furthermore, the fate of the universe is connected to the way cosmic structures like black holes behave. According to theories like Hawking radiation, black holes should emit radiation very slowly, which means they would gradually evaporate over incredibly long periods. Studying black holes and their properties gives us insight into these far-off events. From black holes to light, how does the speed of light affect how we see the universe's end? The speed of light is crucial in how we observe and understand what might happen to the universe in the future. Light travels incredibly fast at about 299,792 kilometers per second, 186,282 miles per second. And this finite speed influences how we perceive the universe in important ways. The speed of light sets a boundary on how far we can see into the universe and, consequently, how much we can learn about its destiny. When we observe distant objects in space, we're essentially peering back in time. For instance, if we see a galaxy that's 1 million light-years away, we're seeing it as it was 1 million years ago because that's how long it took for the light from that galaxy to reach us. This concept, known as look-back time, allows astronomers to study how the universe has changed over time. By observing galaxies at different distances, we can construct a timeline of the universe's expansion and make predictions about its future. However, there's a limit to how far back we can look. The cosmic microwave background radiation, which is the afterglow of the Big Bang, is the oldest light we can detect, dating back to about 380,000 years after the universe began. Before this point, the universe was opaque to light, which means we can't directly see its earliest moments. This limitation also means there's a cap on our direct knowledge of the universe's future, since we can only infer what lies beyond based on our current understanding of physics. In terms of the universe's eventual end, the speed of light means that any observable changes, such as the accelerated expansion caused by dark energy, are seen with a delay. If the universe were heading towards a scenario like the Big Rip, where galaxies, stars, and even atoms are torn apart by the rapid expansion of space, we wouldn't witness these events until long after they've happened. The speed of light also affects our comprehension of events that might signal the universe's end. For example, if a distant galaxy were to vanish or alter suddenly due to some cosmic event linked to the universe's fate, we wouldn't become aware of it until the light from that event reaches us, potentially millions or billions of years later. How would the universe's end impact our understanding of time? The concept of time is intricately linked with our comprehension of the universe, and the way the cosmos eventually concludes would undoubtedly reshape our perception of time. In cosmology, time is often viewed as a linear progression, starting from the moment of the Big Bang and extending into the distant future. While our everyday experience of time is based on clocks and regular routines, the fate of the universe, as predicted by various cosmological models, can challenge and redefine our understanding of time in numerous ways. One fundamental aspect of time is its directionality, often called the arrow of time. This concept is linked to the increase of entropy or disorder in the universe, as described by the second law of thermodynamics. If the universe were to end in a scenario like the Big Freeze or heat death, where entropy reaches its maximum and everything becomes cold and uniform, the arrow of time would lose its meaning. Time would seem to stop because there would be no more change or dynamic processes. Einstein's theory of relativity brought about the idea of time dilation, which means time can pass at different rates depending on an observer's motion or gravitational field. In extreme situations like near black holes or in an expanding universe, time dilation can cause vastly different experiences of time for different observers. As the universe moves towards its end, these effects from relativity would become more noticeable. Quantum mechanics, the theory that governs the behavior of particles on a very small scale, introduces fascinating concepts regarding time. In certain quantum scenarios, time can act in a non-linear or even discontinuous way. If the universe's end involves quantum phenomena, it might challenge our traditional views of time. Some cosmological theories suggest that the universe might go through cycles of expansion and contraction, with each cycle starting with a new Big Bang. In such a cyclic model, time would persist through these cycles, suggesting a more cyclical and everlasting concept of time. In the end, whatever form the universe's end takes, whether it's a freeze, a rip, a graceful fade into darkness, or something beyond our imagination, it prompts us to rethink our understanding of time. It could challenge our usual linear view of time and lead to new philosophical and scientific insights into temporal existence. The universe's end, in all its possible forms, urges us to reconsider our perception of reality. It invites us to reflect on the essence of time itself and the significance of our place within this cosmic narrative. The journey of discovery is ongoing, and the end of the universe is just one chapter in the grand story of the cosmos. As we continue to explore, learn, and dream, we are sure to encounter new marvels and uncover the mysteries of the universe, one documentary at a time. Thank you so much for watching SpaceDrift, and with that being said, take care.